Welcome to the deep dive. We're jumping straight into a really fascinating corner of artificial intelligence today, multimodal AI.
Mhm.
For a long time, AI has tackled information streams separately, text for chatbots, images for object recognition, that kind of thing.
Right. Siloed approaches.
Exactly. But multimodal AI, okay, let's unpack this. It's about AI that can process and understand different types of data together.
Yes. Siloed.
Images, videos, text, audio, much more like how our own human senses work together, right?
Precisely. It aims for a much richer, more complete understanding of the world. If you think about it, only processing one input type is, well, pretty limiting.
Yeah, our daily experience isn't like that at all. It's this constant flow of sights, sounds, words.
Exactly. So multimodal AI tries to mirror that, leading to, hopefully, a much deeper and more context-aware AI.
And that brings us right to our main topic today, Hugging Face's small VLM.
Yeah.
Now, what's really interesting here, I think, is that unlike a lot of these huge AI models,
One's needing massive computing power.
right, small VLM is actually designed for efficiency. They're talking about running it on devices with limited resources.
Which is a huge deal.
We've gathered some great sources for this. There's a really lively discussion happening over on Reddit, plus some insightful blog posts directly from the Hugging Face team.
Yeah, it shows there's a real buzz in the community about its potential.
So our mission today, essentially, is to figure out what makes small VLM unique, what it can actually do, and why it's generating all this excitement.
Especially for people interested in running AI locally, right?
Hmm.
On their own devices. We want to give you a clear picture of this development without getting too bogged down in the weeds.
Okay, let's meet the star then. Small VLM. It's not just one model, is it? It's more like a family.
That's right. Hugging Face has released a few versions. There's Small VLM 256M. They're calling that the world's smallest vision language model.
The smallest. Wow.
Then there's a Small VLM 500M, a bit larger, and the original Small VLM 2B.
Mm.
Even that 2B model is remarkably compact compared to many others out there.
So the core idea, it seems, is this real focus on being small but still packing a punch performance-wise.
Exactly. It's kind of swimming against the current tide of these giant, ever larger AI models we keep hearing about.
The goal being, what, running it on a laptop? A phone?
Potentially, yes. Laptops, maybe even phones or directly in a web browser. That level of accessibility.
Okay, and here's the really attention-grabbing part, the performance claims.
Yes.
Yeah.
They're reporting that the smallest one, Small VLM 256M, can actually outperform their own IDFix 80B model from only about, 17 or 18 months prior.
An 80 billion parameter model beaten by a 256 million parameter one.
Think about that size difference. Hundreds of times smaller, potentially better results. It just shows the incredible pace of innovation right now.
Okay, so how are they pulling this off? It can't just be shrinking things down, surely. There must be some key innovations.
You're absolutely right. It's not just about shrinking. There's several key architectural and training innovations involved. One really surprising finding was about the vision encoder.
That's the part that sees the image, right? Processes the visual input.
Exactly. For the smaller small VLM versions, the 256M and 500M, they found that a smaller vision encoder, it's called a Siglet base patch, 16512, about 93 million parameters.
Okay.
It performed almost as well as the much, much larger 400 million parameter version they used in the original Small VLM 2B.
That's really counterintuitive, isn't it? You'd think more complex vision needs a more complex encoder.
You would, but the benefit here was significant. Using the smaller encoder allowed them to process images at a larger resolution without a massive jump in the compute needed.
So like getting a sharper picture without needing a bigger engine.
That's a good way to put it. It leads to a richer initial understanding of the visual data with minimal overhead, kind of like giving a smaller brain sharper senses.
Clever. What other tricks did they use?
Another big one was optimizing how they tokenize the images. Tokenization is basically breaking the image into chunks the model can understand, like words in a sentence. In the newer small VLMs, they dramatically increased what's called the pixel shuffle. You can think of it as packing way more visual detail into each word or token the AI reads.
More detail per token.
Yeah, they went from about 1,820 pixels per token in the original 2B model to 4096 pixels per token in the new ones. Much richer input.
Okay.
And they also started using single special tokens to mark the boundaries between different sub-images or parts of a larger image.
So instead of using multiple tokens to signal, here's the next part, just one efficient marker.
Exactly. It streamlines the process, lets them handle more visual info with fewer tokens overall. This is really helpful for long sequences, like analyzing different parts of a big document image.
And that helped training too, you said.
Yes, it improves efficiency and stability during training, which generally leads to a better final model.
Interesting. And the training data itself, did they change what the models learn from?
They did refine the data mix for the smaller models. There's a stronger emphasis now on document understanding, about 41% of the data.
Which makes sense for on-device use, right? Processing documents, forms.
Precisely. And image captioning also got a bigger slice, around 14%.
Now, I also saw something mentioned, learned positional tokens. It's a bit technical.
Okay, let's break that down. So when you split an image into patches, the model needs to know where each patch came from, its position in the original image.
Like top left, bottom right, etc.
Right. Initially, they tried using simple text strings, like literally telling the model this patch is top left. But they ran into this problem they called the OCR loss plague.
OCR loss plague, what happened?
The training looked like it was improving on paper, but the model's actual ability to read text in images, the OCR performance, wasn't getting better as expected. It was stagnating.
Tricky.
So to fix this, they introduced these learned positional tokens. Instead of explicitly telling the model the position with text, they let the model learn its own internal representation for top left and how it relates spatially to other parts.
So the model figures out the spatial relationships itself, like developing its own internal map.
That's a great analogy. It figures out the geometry. This turned out to be much more effective, especially for reading text in complex layouts. It fixed the plague, improved training convergence, and boosted OCR performance, which was something people on Reddit were definitely asking about.
Got it. So these smart architectural and training tweaks are the how. Let's move to the what. What can small VLM actually do? The Hugging Face blog mentions some capabilities.
Yeah, even the tiny 256M model is reported to handle things like captioning images, even short videos, apparently, also document question answering, and some basic visual reasoning, like interpreting charts.
And that Reddit thread brought up something really surprising about video, right? Even though it wasn't explicitly trained on video.
This was fascinating.
Yeah.
A small VLM 2B model, despite no specific video training data, did surprisingly well on video benchmarks, even beating some larger models.
How is that possible?
Well, the speculation on Reddit, and it makes sense, is that the model was trained on examples with multiple images, up to 10, I think. And because video data sets often split videos into individual frames, the model might have implicitly learned to process sequences of related images. Maybe the benchmark questions could often be answered just by looking at key individual frames without needing true temporal understanding across the whole video.
So kind of an accidental capability arising from the multi-image training.
Possibly. A clever emergent behavior. Maybe not the original design goal, but still impressive.
It definitely makes you think about how we test these models. What about more formal benchmarks? The AI Models Fair article had some results.
Yes, and those benchmarks really highlight the efficiency. Across different vision language tasks, things like OCR bench for text reading, chart QA for charts, text VQA and doc VQA for Q&A on text within images and docs, even video tasks like video MME and MLVU.
Small VLM holds up well.
It performs strongly, especially when you factor in the resource usage. The killer feature is the low RAM requirement. That 256 mem model needs less than 1 gigabyte of GPU RAM for single image inference.
Less than 1 GB, compared to what for bigger models?
Oh, easily 24 GB, 48 GB, or even more for some of the giants. It's a massive difference. Really drives home the efficient part.
Absolutely. But the Reddit thread also had that user sharing their real-world experience, noting some variability in response times.
Right, that was an important point. The user with the RTX 8000 Quadro GPU, they mentioned that while small VLM could be accurate, the generation time sometimes varied a lot, even for short answers.
And they suspected their older GPU architecture might be involved.
Yeah, they wondered if their Turing architecture wasn't fully optimized for some techniques small VLM uses compared to newer Ampere GPUs. It's a good reminder that efficient is relative, and performance can still depend heavily on your specific hardware setup.
It shows the value of that community testing and feedback loop.
Definitely. People sharing configurations, results, issues. It's how these things get ironed out.
Speaking of issues, what about the OCR capabilities that kicked off that Reddit thread? Sounded like there were some specific observations there.
Yes. The initial user found it was pretty good at reading focused text blocks, like a single paragraph. But it struggled more when trying to read, say, an entire computer screen full of text all at once.
Okay, so focus matters.
It seems so. Another user chimed in, pointing out you can adjust the input image resolution for the model. There's a parameter N you can tweak, Increasing N gives the model a higher res view.
But that caused an error for someone else.
Right, someone tried increasing N locally and hit an error, but then very quickly, a Hugging Face researcher jumped into the thread.
Oh, cool.
And said, yeah, that was a known issue with the default value, and it was already fixed in their internal development version.
That's great responsiveness.
It really is. Shows active development and community engagement. The general takeaway seemed to be, OCR is promising, but you might need to play with the resolution based on the task and your hardware limits.
Right. So moving beyond benchmarks and the specific user tests, what about real-world applications? What's being explored or envisioned for small VLM?
Hugging Face mentioned a few interesting ones. There's something called Call Small VLM. It's designed for efficient, multimodal retrieval.
Retrieval, like searching.
Exactly. Imagine searching through huge data sets using both text and image queries, but doing it really fast and cheap because the model is so small.
That could be powerful.
Then there's Smoldocling, an even tinier version specifically for document processing tasks. Ultra compact.
Makes sense. And BioVQA.
Yeah, that one's focused on biomedical visual question answering. Think interpreting medical scans, answering questions about them, a specialized high-stakes area where efficiency could be key.
Those all sound incredibly practical, especially for offline use or places without massive cloud resources. What's the feeling on Reddit about these applications? What are people excited to maybe build?
Oh, the enthusiasm is definitely there. You see people talking about creating GGUF models.
Which make it easier to run on different kinds of computers.
Exactly. Broader hardware compatibility, especially CPUs. There's also a lot of buzz about Android apps. Imagine having a capable VLM running locally on your phone.
Like a visual assistant in your pocket.
Kind of. One user even mentioned their existing text-based LLM app, PocketPal, and was dreaming about integrating vision capabilities using something like Small VLM. That would be transformative.
I can see that. Any comparisons to other small models?
Yeah, people were comparing it to models like MiniCP v2.6 and especially Moondream.
Ah, yes, Moondream. What was the verdict there, based on the thread?
Well, the Hugging Face researcher offered a perspective. They said comparing Small VLM to the currently available open-source Moondream models, Small VLM seems to give generally more accurate and richer answers.
Okay, based on what's publicly available now.
Right. They acknowledge the Moondream team is working on newer, perhaps closed-source versions that might be better, but you can't really compare those directly yet.
Got it. So if someone listening is intrigued and wants to try Small VLM out, how easy is it to get started?
Hugging Face seems to have really prioritized accessibility. The models are available through the standard Transformers library, which tons of people use.
That's convenient.
They also support MLX for Apple Silicon and ONNX for broader deployment. Plus, they have WebGPU demos you can just run in your browser.
No complex setup needed for the demos.
Nope. And the blog posts even include simple code snippets to get you started with inference using Transformers or MLX. They've lowered the barrier to entry quite a bit.
That's fantastic. It really does feel like Small VLM is pushing the envelope on efficient AI. Okay, as we wrap up this deep dive, what are the main takeaways for our listeners?
I think the biggest thing is that Small VLM is a major step towards making powerful multimodal AI much more efficient and accessible. It proves you can get impressive capabilities in a tiny package.
Thanks to those innovations in architecture, training, tokenization.
Exactly. And the performance relative to its size and resource needs is, frankly, quite surprising. It challenges that bigger is always better mindset in AI.
Absolutely. And for you listening, if you want to stay updated on AI advances without getting overwhelmed, Small VLM is a perfect example. It shows cutting-edge research becoming practical, maybe even ending up on your own devices soon.
Which leads to a really interesting thought to leave you with. Given this kind of efficiency, Small VLM's efficiency, what totally new kinds of on-device AI applications might pop up?
Applications that blend seeing and understanding text locally.
Right. Imagine AI that can truly see and understand the world around you right there on your phone or laptop. No constant cloud connection needed. What possibilities does that open up?
That is a fascinating question to ponder. Thanks for joining us for this deep dive into Small VLM.
My pleasure.
Until our next exploration.